Hey there, Space Cadets! Today we're diving into the mind-blowing world of Minkowski Spacetime. Buckle up because things are about to get seriously cosmic. But first, let's rewind a bit. Remember Einstein and his groundbreaking theories of relativity? He totally revolutionized our understanding of gravity. Einstein showed us that gravity isn't some mysterious force acting at a distance. Instead, it's all about the curvature of spacetime itself. Massive objects like stars and planets actually warp the fabric of spacetime around them. Imagine a bowling ball placed on a trampoline. The ball creates a dip, right? That's kind of how massive objects warp spacetime. Now, imagine rolling a marble across the trampoline. It wouldn't travel in a straight line, would it? It would curve around the bowling ball due to the dip. That's how gravity works. Planets orbit stars because they're following the curves in spacetime created by the star's mass. It's a cosmic dance dictated by the geometry of the universe itself. Before we journey into the fourth dimension, let's revisit the familiar territory of the first three. Imagine a straight line. That's one dimension, folks. A line only has length. Now add another line perpendicular to the first one. Boom! You've got yourself a two-dimensional plane. Think of it like a flat sheet of paper. It has length and width. Our world, however, is a bit more exciting. We live in a three-dimensional world, a world with height, width, and depth. Picture a cube. It exists in three dimensions. We can move left or right, forward or backward, and up or down. These three dimensions define our spatial reality. But what if I told you there's more to the story? What if there's a fourth dimension lurking beyond our perception? Hold on tight, because this is where things start to get really wild. The fourth dimension isn't like the first three. It's not another direction we can point to. It's time. Yeah, you heard that right. Time, my friends, is the fourth dimension. But it's not time as we usually experience it. We're talking about time as a dimension intertwined with space itself, creating a unified fabric called space-time. This concept is hard to wrap our heads around because we experience time linearly. We move from the past to the present to the future, seemingly at a fixed rate. But what if our perception of time is just a tiny slice of a much grander cosmic picture? What if time, like space, can be stretched, compressed, and maybe even traveled through? Get ready to enter the mind-blowing world of Minkowski Spacetime. Okay, I know thinking about time as a dimension can make your brain hurt a little. So, let's try an analogy. Imagine you're a flat, two-dimensional being living on a piece of paper. Your entire universe is that flat surface. You can only move left or right, forward or backward. Now, imagine a three-dimensional being, like us, approaching your 2D world. From your perspective, you wouldn't be able to see the entire 3D object. You'd only see a 2D slice of it as it intersects with your plane of existence. If a sphere passed through your world, you'd first see a point, then a circle that grows larger, then smaller again, and finally another point before it disappears. You wouldn't perceive the sphere as a whole, just its 2D cross-sections. Section 5. Minkowski Spacetime. A new reality. That, my friends, is kind of how we, as three-dimensional beings, experience the four-dimensional fabric of spacetime. We see snapshots of events, moments in time, but we don't perceive the entirety of spacetime. That's where Hermann Minkowski comes in. This brilliant mathematician, a contemporary of Einstein, gave us a way to visualize and understand this mind-bending concept. Minkowski developed a mathematical framework that combined space and time into a single entity, spacetime. In Minkowski spacetime, time is not absolute. It's relative, just like Einstein proposed. The rate at which time passes depends on your relative motion through space. This might sound crazy, but it's been experimentally verified countless times. Section 7. Moving through spacetime, a cosmic dance. Here's where things get really interesting. Remember how massive objects warp spacetime? Well, that warping affects the worldlines of objects moving nearby. It's like placing a bowling ball on a stretched rubber sheet. The ball creates a dip, and any objects rolling nearby will curve toward it. The same thing happens in spacetime. The closer you are to a massive object, the more your worldline curves. This curvature is what we experience as gravity. But here's the mind-blowing part. As you move through spacetime, you're not just traveling through space, you're also traveling through time. And the faster you move through space, the slower you move through time relative to someone who's stationary. This is called time dilation, and it's one of the most bizarre consequences of Einstein's relativity. Section 8. Light cones, mapping possibilities in spacetime. Now let's talk about light. Light plays a crucial role in Minkowski's model because it travels at the cosmic speed limit. The speed of light, approximately 299,792,458 meters per second. Nothing in the universe can travel faster than light. In Minkowski spacetime, we can represent the paths of light rays as cones, called light cones. Imagine yourself at the very tip of a cone. The cone represents all possible events in spacetime that you can influence or be influenced by. The upper half of the cone represents your future. These are the events you can potentially reach, depending on how fast you travel. The lower half of the cone represents your past. These are the events that could have influenced you. The surface of the cone represents the paths of light rays emanating from and arriving at your current location. Section 9, Relativity's Twist. Different perspectives on events. Here's where relativity throws us another curveball. Events that are simultaneous for one observer might not be simultaneous for another observer who's moving relative to the first. This is called the relativity of simultaneity. It's one of the most counterintuitive aspects of special relativity. Imagine two events, a firecracker exploding on Earth and another firecracker exploding on Mars. For an observer on Earth, these events might seem to happen at the same time. But for an observer on a spaceship traveling at a significant fraction of the speed of light, these events might happen at different times. This is because the observer's motion affects their perception of time. It's like looking at a moving train from different angles. Your perspective changes what you see. Section 10. The speed of light, a cosmic speed limit. So we've established that nothing can travel faster than light. But why is that? Well, in Minkowski spacetime, the speed of light is more than just a speed limit. It's a fundamental constant that defines the relationship between space and time. As an object approaches the speed of light, its mass increases infinitely, and time slows down to a crawl relative to a stationary observer. To reach the speed of light, an object would need an infinite amount of energy, which is impossible. So for now, faster-than-light travel remains firmly in the realm of science fiction. But who knows what the future holds? The universe is full of surprises, and our understanding of space-time is constantly evolving. Section 11. Time travel and beyond, the future of space-time. Speaking of the future, let's end with a tantalizing thought: time travel. Could it be possible? According to Einstein's theories, time travel might not be as far-fetched as it seems. Remember those wormholes we talked about earlier? Some physicists believe that wormholes could act as shortcuts through space-time, connecting distant points in space and time. Imagine stepping into a wormhole and emerging in another galaxy, or even another time. Of course, this is all highly speculative, but the study of Minkowski spacetime opens up a universe of possibilities, from time travel to parallel universes and beyond. The journey through spacetime is far from over. In fact, it's just beginning. Stay tuned for more mind-blowing explorations of the cosmos. Thank you for watching. If you enjoyed this video, please like, share, and subscribe to our channel for more fascinating content on the mysteries of the universe.